So with this lecture, we start a new topic, which is frequency response of transistor amplifiers. So until now, all the transistor circuits we analyzed, we had neglected the effect of capacitors. We had assumed them either to be short circuits, which was the coupling and the bypass capacitors, and implicitly we had assumed that the internal transistor capacitances were open circuits. We will see this in just a minute, how this was assumed implicitly. So now we go to the next level of our amplifier analysis and include capacitive impedances and see how they affect amplifier behavior. When capacitances are included, what that would do is that there will be the 1 over j omega c or 1 over sc, and so the amplifier parameters gain, input resistance, output resistance will have omega in their expressions, and so they'll all become functions of frequency. Okay, so to begin with, let us look at two capacitances that are part of a PN junction. We may have very briefly talked about this earlier, but this is just a slightly longer description of the capacitances. So the PN junction has two capacitances internally. One is called the junction capacitance. I'm calling it CJ, different people call it different things. This capacitance appears due to the charge stored in the depletion region of the PN junction, and after solving Poisson's equation for a PN junction, one can show that the junction capacitance has this big expression. It actually has the same form as a parallel plate capacitor, which is an interesting thing, which we will not discuss. Epsilon A by W, where W is the depletion layer width of the PN junction. So in this expression, A is the cross-sectional area of the PN junction, Q is electronic charge, epsilon is epsilon 0 times epsilon S, where epsilon 0 is the dielectric permittivity of vacuum and epsilon S is the relative dielectric permittivity of silicon, because we are assuming silicon as our material. VBI is called the built-in voltage of the junction. It's an internal PN junction parameter. VD is the applied diode voltage across the diode. This is ND, which is the doping density on the N side. So this equation is written actually assuming that in a PN junction, the N side doping density is much lower than the P side doping density, and then this is the expression. If both densities are similar, this expression is a little longer, but we will not worry about it. In a bipolar transistor, actually, both the junctions, in an NPN transistor, the base emitter and the base collector junction, one side is much more lightly doped than the other side, and this will be the density of the lightly doped side. In any case, we are not ever going to use this expression for this course. This is just for your information that this expression looks like this. In fact, actually the only thing I want to point out about this expression is that the junction capacitance of a PN junction is a function of the square root of 1 over the applied voltage. What this means is that the capacitance is a nonlinear capacitance. It is not a linear capacitance, because a linear capacitance would be independent of the voltage applied across the capacitor. But here, because the capacitance is a function, this makes it a nonlinear capacitance. Okay. The other capacitance of a PN junction is called the diffusion capacitance, and this appears due to minority carriers injected in a PN junction when it is forward biased. So when a PN junction is forward biased, holes from the P side are injected to the N side and they become minority carriers, and some of them kind of form a stored charge, and similarly electrons on the P side. For a bipolar transistor, the expression for the diffusion capacitance is this, where Gm is our transconductance as IC over Vt. Wb is the width of the base region. So you have a collector, base, emitter. Wb is the width of the base region. dB is called the diffusivity of minority carriers. D is the diffusivity. This dB refers to the diffusivity of minority carriers in the base. So in an NPN transistor, the base is p-type. So dB will be the diffusivity of electrons in the base region. This quantity Wb squared over 2 dB is often also called the transit time, tau t or tau b. That's all. Yeah. So you can actually see the dimensions, right? The capacitance is conductance times time. So conductance goes to this side, will become resistance. Anyway, so C diffusion is also not a linear capacitance. How? Because C diffusion is a function of the collector current, and through the collector current, the voltage in the transistor. So it's not a constant. It varies as the collector current varies. Okay. If one does the numericals, one finds that, well, of course, in reverse bias, the junction capacitance dominates, because in reverse bias, there is no diffusion capacitance because there are no injected carriers. In forward bias, it turns out that compared to Cj, C diffusion is much larger, and so it dominates. In an equivalent circuit, both of these will come in parallel with each other, and in parallel with basically with the intrinsic diode or the junction, NEPN junction. Okay. So for a bipolar transistor, because there are two junctions, there are two sets of capacitances. There is a base emitter capacitor and a base collector capacitance corresponding to each of the junctions. Each capacitor consists of the sum of the junction capacitance and the diffusion capacitance. And in the active mode, which is base emitter forward biased, base collector reverse biased, the base emitter capacitance will be dominated by its diffusion capacitance. The base collector capacitance will be dominated by junction capacitance. In the small signal model, these are represented or called C pi and C mu. So this is what we will use throughout our analysis, only the small signal capacitance, and we'll assume them to be constant, because for small signal we have, by definition, for small signal the DC quantities or the large signal quantities are assumed to be constant. So C pi, for example, is a function of the collector current. So we'll assume that there is a constant DC current flowing, and therefore C pi is constant. Also, for our purposes, we'll simply assume that C pi and C mu are the values are given to us. So we won't even calculate them based on the formulas that I showed you in the previous slides. Okay, so with this, now we are ready to analyze circuits. So first we include these capacitors in the hybrid pi small signal equivalent circuit. So the earlier the circuit had an R pi and a beta IB. Now there will be a capacitance between the collector and the base, so C mu, and between the base and the emitter, C pi. So this becomes our high frequency equivalent circuit. Incidentally, I may or may not have mentioned this before, but if we look at this beta IB and we look at IB, so IB is the base emitter voltage divided by R pi, VBE divided by R pi. So if we write beta IB as beta VBE by R pi, then we know that beta by R pi is defined as GM. So beta IB can be written as GM VBE, and therefore this equivalent circuit can also be written like this. So we define the base emitter voltage as VBE, and this is GM VBE. Sometimes this is more convenient because now we have two things in parallel. So the base emitter voltage is an easier quantity. Every time trying to find the base current is a little more hassle. And especially if you are doing nodal analysis, which is what we usually do, voltages are easier to deal with than currents. So we'll use this circuit, the same as this, but we'll use this form of the equivalent circuit for our analysis. Alright. So let's start with our first circuit and then do a frequency analysis of this circuit. So I have chosen this circuit as our first circuit. So it's a common emitter amplifier with a bypass capacitor, and it has a source resistance. The source has a source resistance. Without the source resistance, the analysis becomes a bit too simple. So I've included this so that it is reasonably rigorous. Okay. So I've put some values. So all the resistance values are given. The capacitance values are given. I'm saying let beta be 200. Let the emitter capacitor, which is large, be 2 millifarads. Let C pi be 4 picofarads and C mu be 1 picofarad. This is typical. Pico is typical of bipolar transistors, and of milli is typical of the bypass capacitor. So the first thing we do is analyze this circuit under DC conditions. So we short this AC source. So this is 0. So there will be some small current flowing through the base, but because this resistor is small, I'm saying let us start with the assumption that the base voltage is 0. That is, the voltage at this node is 0. If this is 0, then VE is 0.7 volts. So this is 0.7 volts. So of course CE is open for DC. So the current in RE is 0.7 minus 0.7. I'm sorry. So this is minus 0.7. Let's change this. This is minus 0.7. So the voltage across the emitter resistor is 11.3 volts. And the value is also 11.3 kilo ohms. So the emitter current and collector current are about 1 milliampere. Collector resistor is 6 kilo ohms, so 6 volts across RC. So the output DC voltage is 6 volts. So 1 milliamp gives us a base current of 5 microamps because there is a beta of 200. And so if we calculate the actual value of VB, the DC voltage, it will be minus 5 millivolts because the source resistance is 1 kilo ohm. And so we say, well, 5 millivolts is small enough, and so our assumption was 0 was reasonably correct. Alright. So this completes our DC analysis. For reference or for future use, we find the AC quantities also. So R pi is VT over IB, 25 millivolts over 5 microamps, which is 5 kilo ohms. GM is IC over VT, 1 milliamp divided by 25 millivolts, which comes out to be 40 milliamps per volt. And GM RC, the product, is 240. Alright, so now let us draw the small signal circuit including capacitors. So here it is. So this is our actual circuit. This is the small signal circuit. So VS, RS, RE, CE, RC, and then the rest of it, C pi, C mu, R pi, GM, VBE. Now notice that I'm not making any assumption about CE being a short circuit because now we want to find the effect of CE as a function of frequency on this circuit. So now there are 3 capacitors here. Alright, now let's look at some numericals a little bit. Let's look at a low frequency and a high frequency. So let's say if omega is 100 radians per second, a reasonably low frequency, let's find the magnitudes of the 3 capacitive impedances. So CE is 2 millifarads, so times 100, so if 100 times 2, 0.2, so this gives us 5 ohms. So the impedance of the emitter capacitor at 100 radians per second is 5 ohms. C pi is 4 picofarads, pico, very small, frequency is small, capacitor is small, so this turns out to be 2.5 giga ohms. Cu mu is 1 pico, 1/4 of C pi, so this is 1/4 of 2.5, 625 mega ohms. Then if we find the impedances at a large frequency, let us say 300 mega radians, then omega is large, so this is going to become very small, so it turns out to be 1.7 micro ohms. This turns out to be 833 ohms, and this is 208 ohms. So if we look at these numbers, what we conclude is that at low frequencies, low is qualitative here, I am not quantifying it right now, this is just some representative number, but we say at low frequencies, C pi and Cu mu are very large, alright, C pi and Cu mu are very large. Now let's look at this figure here. C pi is in parallel with R pi, and C mu is actually not in parallel with anything, but we'll just compare it with other resistors in the circuit. So this, if this is a giga ohm and R pi we saw was 5 kilo ohm, we say that this C pi is far greater than R pi, and therefore at those frequencies no current will flow through C pi. It is 10 raised to 6 times larger than R pi. So we say, well, this basically acts as an open circuit. Similarly, this is also very large. So compared to, so if you look at current coming in here and now C pi is not there, the current can either go down or it can go into C mu, but C mu is far greater than R pi in its impedance. So we say that no current will go through C mu also, or well, a very, very small current will go, and therefore effectively we assume that C mu is an open circuit at low frequencies. Alright, and so we can ignore, while doing a low frequency analysis, C pi and C mu. Ce of course stays, so Ce is 5 ohms, of course that is much smaller, so it will stay. Okay, go back. At high frequencies, this is a micro ohm compared to how much is this? 11.3 kilo ohms, it's here. So we say, well, this is very small compared to this, and therefore we can ignore this. Or we can say, well, this is what we did when we did the analysis earlier. We'll say that micro ohm is equivalent to a short circuit. So we'll assume that Ce acts as a short circuit at high frequencies. So I'm just saying high, we'll define high and low later on. But we can say that low frequencies, C pi, C mu can be ignored. At high frequency, not ignored, can be treated as open circuits at low frequencies, and at high frequencies, C can be treated as short circuit. So what we'll do is we'll analyze this circuit in two different domains, one for low frequencies, another for high frequencies. Alright, and then later we'll show that this is an okay thing to do when we put the actual numbers. Alright, so we'll start by, so we'll analyze this circuit twice, low frequencies and high frequencies. So let us start with low frequencies. So for low frequencies, we ignore this, open circuit, the C pi and C mu, and this is the circuit we get. And that has now only one capacitor. So now let us analyze this circuit and find its voltage gain, which is VO over Vs, including the effect of Ce. And now we'll write Ce as I had done maybe about 11 lectures ago, I don't remember. We'll write this as 1 over S Ce rather than j omega. We'll go back to j omega. This is just more for convenience right now than anything else. Alright, so given that, now this is not a difficult circuit, it has 3 nodes. So we have to write 3 nodal equations, as we've seen before, this nodal equation is trivial. So VO is equal to minus GM RC VBE, GM VB times RC. So basically I have to write these two nodal equations and solve them. So they are written here. So at the base node, we write VB minus Vs by Rs plus VB minus VE by R pi equal to 0. And if we multiply out by Rs R pi, then we'll get one equation in VB, VE and Vs on the right side, because Vs is a known quantity. At VE, we'll have VE minus VB by R pi plus VE by RE plus SCE VE, because this is VE over 1 by SCE, minus GM VB, 4 terms equal to 0. So we write that here. Again, we multiply out by R pi RE and we combine terms. So there is only VB and VE in this equation. So we'll get this big equation. Now note that this equation has GM R pi, and GM R pi is equal to beta. So this is actually 1 plus beta RE. This is also 1 plus beta RE. Alright, so we've got two equations. This here VB VE, another here VB VE. We have to solve. Okay, so I'm not solving this because there's no point solving it on a PowerPoint. So I've just written the final answer here. I want you must solve this at home. Solving such circuits is an absolutely essential aspect of learning amplifier analysis, and you have to solve many such circuits to become used to solving them. I'm just writing the answer here. So this is the answer, and this is written. I have written it in a particular form. So I'm saying VO over Vs is a constant multiplied by S plus a constant divided by S plus another constant. Alright, there are many ways of writing this equation. This is kind of what I call a standard form of writing a low frequency transfer function. So the standard form is a constant and then a ratio of polynomials, a numerator polynomial, a denominator polynomial. In our case, it happens to be only a first order polynomial. This is actually a direct consequence of having only one capacitor in the circuit. If there were two capacitors, both of these will be quadratics. Okay. So now let us convert S to j omega, and so just the same thing is written here with S replaced by j omega. And let us study this for a little bit. So we want to find this expression for extremely low frequencies. Extremely low. Alright, so let's look at this expression and say, oh my guys, extremely low. If it is extremely low, then we can say that compared to this term, or let us define low as the magnitude of omega is much less than 1 by CERE. And therefore it is also much less than this quantity. So if omega is much less, then we can say that these j omega terms can be ignored compared to these two terms, and then we are left with this and this, which is what I have written here. And then if we simplify, so the CEREs cancel, and then the R pi plus RS cancels, and so that is here, the R pi plus RS cancels, and we end up with this. So we get VO over Vs equal to this. Now I don't know if this rings a bell, but this in fact is the voltage gain we had derived for this circuit without CE. If CE is not there, we had RC, RE. Okay, RS you think about. We didn't have RS, but some magically RS is not there, so you think about. But this expression is familiar. Alright, and then we had said that in the denominator R pi can be ignored compared to beta RE, and then GM R pi is beta, so beta cancels, and you get minus RC by RE. So we've seen this before. So this is the expression of the voltage gain of the circuit without C. and it should be like that. So this reduces to an expression without CE at very low frequencies. So what happens at very low frequencies? The capacitor acts as an open circuit, and therefore we can ignore it and we get our expression which we have derived earlier. Alright, now let us see what happens at high frequencies. Alright, and what is high? So let's look at this expression. We say omega is much greater than this, and we say omega is much greater than this also. Then we say because this is much greater, we ignore this constant term, we ignore the constant term compared to the j omega, and then here we'll just get j omega by j omega, and so that is just 1. So the gain we get is minus GMRC R pi by R pi plus RS. This also is familiar if you remember from lecture 11. In lecture 11 we had derived the expression for, let us see, this with the capacitor shorted. So if this is short circuited, we have minus GMRC as the gain, but if we put a source resistance, then loading occurs and the base voltage is R pi divided by R pi plus RS into Vs. So the gain will be R pi divided by R pi plus RS into GMRC, which is what is here. So this is the gain if the capacitor acts as a short circuit, which is at high frequencies, right? At high frequencies, CE becomes short circuited, and then we get the gain corresponding to a short CE. So this was also expected. Now let us see what happens between these two frequencies, the low and the high. For that we draw a Bode plot. So which is kind of a repetition of what we just discussed, but we kind of repeat it for the sake of drawing a Bode plot. Okay, so to draw a Bode plot, let us simplify this. So this is the expression again. So I'm writing this in a simpler form. So let's call this constant term as AVM, though it is called the midband, M for midband, V for voltage. So the midband voltage gain. Let's call this quantity as ZL, 1 by CERE, and let's call this big quantity as PL. Z for 0, P for pole, L for low frequency, because we are doing the low frequency analysis. I'm calling them ZL and PL. Alright. So this transfer function has 1, 0 and 1 pole. Now let us draw a Bode plot of this. But let us notice that for this expression, PL is greater than ZL. Can you see that? This denominator is greater than the numerator. So the CERE is common, which means that this term, the denominator term, is greater than 1. Can you see that? Well, because beta is here, so beta RE is much greater than RS. RE, RS are of the same order, so this term is greater than 1. So that's why PL is greater than ZL. Alright, so with this information, let us draw a Bode plot. So, okay, so this is the expression, and this is the first part of the Bode plot. So we know that PL is greater than ZL, so we put ZL and PL here. Then we say for extremely small omega, as I said, we are repeating this, extremely small omega, these two terms can be ignored and the voltage gain can be written as AVM ZL over PL. AVM ZL over PL. So up to say up to ZL, until ZL is reached, or omega less than ZL, much less than ZL, and therefore much less than PL, this holds. So that Bode plot, we do kind of a piecewise linear thing. So we'll extend this till ZL and say the gain up to ZL is this AVM ZL by PL. And then we say, well, what happens? Let's see what happens next. So we say for frequencies in the middle range, omega greater than ZL but less than PL, omega greater than ZL. So for an approximation, we say we'll ignore the ZL in the numerator. Omega is less than PL, so we'll ignore the omega in the denominator. So we'll get j omega by PL. So the magnitude will be omega by PL. and so the gain varies linearly with omega here. Alright, and we've seen this before when we discussed Bode plots much before. And so if you were, so this is of course a dB gain versus log of frequency plot. So on this plot also this will be a straight line, and the slope of this will be plus 20 dB per decade. So it will go, and we'll draw this up to PL, although this is actually valid only for much less than PL. As we said, we are doing a approximate piecewise linear analysis. Okay, and then for omega much greater than PL, then it is also much greater than ZL. So these both go, j omega cancel, and we get AVM, and it's a constant. So for omega greater than PL, we get a constant gain. So this is our Bode plot of our low frequency transfer function. So what we see is that if you were to come from here, so this is the region we had analyzed for our common emitter amplifier with a bypass capacitor. So we said the gain was GMRC into R pi by R pi plus RS. Now what we kind of recognize is that because of CE, the gain, as the frequency reduces, the gain will start falling to a lower value at the pole frequency PL. It will keep falling until the zero is encountered, which is ZL, and then it will become a constant again at a lower value corresponding to the emitter capacitor being open circuited. So this is short circuited higher gain, open circuited lower gain, and in between it will drop. So now we have a much more comprehensive and a nicer picture of this circuit as a function of frequency. As I said, this is an approximate plot. Bode plot is approximate. The actual plot will be more continuous and kind of do like that. And here it will be, the actual gain will be 3 dB below the maximum gain. We've seen this before. And here the gain will be 3 dB higher than the lower gain. Okay. So for this completeness, let us find the numbers for these three quantities, AVM, ZL and PL. So you can do this at home. I've just written the numbers. So the common emitter gain is 200. It was 240 GMRC, but because of loading, it has become 200. ZL is 7 millihertz, a very small quantity. PL, the pole, is 2.8 hertz. So below 2.8 hertz, the gain will start falling. Alright. Okay. So next lecture, we'll discuss the high frequency response. For now, this is it.